The second button is start recording. So what I'm doing right now is I'm streaming everything that you see on the projector and my voice to YouTube. All right, so let me minimize this. And then you can go to YouTube, and you can do it even now on your cell phone or whatever device that you have. And then you can go to youtube.com and then go straight to my channel. My channel is Somprofs, SOMEPROFS. So this is one thing that you might want to write down, because once you can get there, you can get everything else, because everything else is being screen recorded. Okay? All right. So once you get there, you go to the Videos tab, which is right here, and it will show you all the videos that I have recorded over the past 5 years or so. I think I have 2,300 and something video clips. Each one is about 80 minutes long. But so far, Google has not complained, so I'm not going to delete anything. So if you want to, you can go all the way back in time and find out, how I taught this class like maybe 3 to 4 years ago. But that takes a lot of time. I really doubt anyone would have time to do that. This is the one that we are recording right now. So if you click on that one right now, you will actually see the content of the class, but it has about a 20-second delay or lag time. So you can see it's really just doing about the same thing. And eventually you will see, yep, right there, which is what I did about 20 seconds ago. So it is live streaming, which means I don't need to save the file and then upload later, which was what I have been doing before. Now it is just, there to begin with, which is really useful because, by the time we get to the lab, the lecture is already recorded. It's already online. So when you're doing your lab and you go like, I kind of need to remember what text said about blah, 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 you can actually refer back to the video during the lab time. The only thing that's going to be missing from the video is the closed captioning. So closed captioning won't be there until maybe a day after. Okay, so if you rely on closed captioning, that would not be there in the lab. But you can bring your own headphone. You can listen to the lecture from your cell phone, from the computer in the lab, and stuff like that. So there are plenty of options there. Okay, and you can also see the effect of a mirror in the mirror. And it takes 20 seconds or so to get another embedding of the image. It's recursion, basically. And this is infinite recursion kind of thing. All right. So are we good so far? Where to find the screen recording of this class? Okay, because that's your number one resource if you need to review content or just want to kind of go like, okay, what did Tech say about the final exam? Okay, if that's something that I talked about in class, if it's recorded, it's going to be on YouTube. Cool. I got Clever Clover as a subscriber. I got about 400 plus, but I never monetize my channels. So you don't have to worry about, advertisements and stuff like that. They pay me well enough here. All right, so everything about this class is on Canvas. I think you guys have access to Canvas for this class now. Yes? Okay, so I saw a few nods. Okay, that's good. Because for the CISP 440 class, I accidentally set up the wrong start date of the class. So, people were not able to access the class, and I had to go check and go like, why are they not accessing the class? It turned out to be my mistake of using the wrong start date. All right. So we'll start with information that is specific to this section, and then we'll go over some other stuff. All right, section-specific information, this is copied from the schedule, so there should be nothing surprising here. Okay, this is the Tuesday, Thursday class, basically from 9 to noon, 4-unit class, and you might want to kind of take note of when is the last day to drop without a W, and when is the last day to drop with a W. So those two dates are particularly important. The rest of it, this portion at least, is what we call the student learning outcome. Every professor of every single class should include this in the syllabus now. Basically, it's just a description of what you should be able to do at the end of this semester, assuming that you're passing with a letter grade of C or better. Okay? And then the rest is really just a proposed schedule of what I plan to talk about in this class. I tend to kind of move along slightly differently, so if I'm not on topic of a particular date, don't worry, okay? Eventually I will get back to it. All right, so are there any questions at this point? No questions? Now, one thing that you might want to do is to print out the schedule along with the next part that I will be talking about. Depending on which school you're transferring to, sometimes we do not officially articulate this class with that campus. So in that case, they would want to look at a list of topics along with the syllabus. So instead of emailing me like 2 years from now, and then say, okay, I need the syllabus, when I took this class, which I might have problem digging up, it's better to have a copy with you. And the same goes for many of your other classes. So any other classes where you think, oh, I might want to transfer this class, not just to unit, but having this class being equivalent to another class at a 4-year university, you might want to keep the syllabus and most of the paperwork with you in case, the other 4-year university says, I want to look at your the last few projects of that class. Then you can present and go like, okay, this is what I did as the last project of that particular class. So the other professor can now assess and go like, okay, this is about the same as what we teach here, and we can look at this class as equivalent to our class here. Does it make sense? Okay, so organization can be kind of useful. You can also scan all of this, just print it out as a PDF, push it onto your own Google Drive. Okay, that works too. But keep a copy. Okay, just try to keep a copy of everything that you do because they might come in handy in the future. Is that okay? All right. Okay, so I'm going to move on. So the next portion is the so-called syllabus, but it's not really a syllabus. It's basically either you can click on the PDF. So once again, if you want to print it out, put it into a binder, click on the PDF. On the other hand, if you want to just kind of read it from your cell phone, the HTML version is much more friendly for that purpose. So this is nothing more than a common part of my syllabi for all of my classes. So instead of generating one individual syllabus for every single class, I just break it up. One section that is dependent on the section itself, and the other part that is common to all of my classes. Is that okay? All right. So I'm not going to read out this entire thing. What I will do is to go over just a few things that I think is important even on the first day of class. So this is the first one, your first day of class or orientation. Basically, it says, any absence on the first day of class is sufficient reason to be dropped. Okay, so if you're here, physically, you don't have anything to worry about. I'll take a roll later, okay? On the other hand, if you're watching this live, on YouTube from home, you might have something to worry about then, okay? So that's one. I'll just kind of go over the other ones. Etiquette policy, or let me go back to classroom behavior expectations. Basically anything that's disruptive, disrespectful, and so on and so forth would not be tolerated. But if you have questions, please feel free to raise your hand. Okay, as long as what you are asking or what you're going to comment on is related to class material, I don't have any problems. So we can have a class discussion if we need to. Okay, that's probably a good thing to do. Chatting seems to me is the biggest problem. Okay, and most of the time it's not even malicious. Okay, it's not disrespectful. It's just one person couldn't quite get what I said a little bit earlier. I flip the screen, and then that person go like, okay, but I didn't have time to write it down. And that person asks, another person is like, okay, did you write down what Tech wrote down a little bit earlier? That can be distracting, okay? Not only to the student that is being asked, but also to people who are around, those students. So instead of asking the other student, what was in the previous screen, just raise your hand, and I'm more than happy to kind of flip back to the screen or do something similar, okay? That's about the only thing I need to go through. The rest of this is presented in a video. So I'm trying to do things a little bit differently this semester. So I made a YouTube video presentation of the syllabus, of the common part of the syllabus. So you need to watch this presentation. Okay, it's only about half an hour long, but instead of taking half an hour of class time, I'm going to have you guys watch this and basically go through the syllabus. So open up the PDF or the HTML document on one side and then watch the presentation on the other side. If you have any questions about the syllabus, let me know either during my office hour, which is right before this class, very handy for you guys, or you can send an email to me or message me through Canvas. So let me know if you have any questions or concerns about the syllabus. Otherwise, I'm going to assume that you are going to, one, you know where to find the syllabus, and you are going to read it. Okay? Would that be an okay assumption? All right. Let it be recorded that I did not see anyone objecting to that. Because there's no webcam to look at you guys. Do you guys want a webcam? No? Because I can put a webcam here so I can actually see the whole class nodding. Okay. All right, so this class has a unique problem. Okay, it's not too much of a problem, but it is an issue. On the wait list, I think I got about 17 people on the wait list. The problem is the lab only has 29 seats. So I cannot exceed that number. All right? Huh? You can sit on the ground, but the fire marshal would not let you do that. So, I do have a Monday, Wednesday class. You probably got that email already. I do have a Monday, Wednesday class from 10:30 to 1:30. That's basically the same as this class. So if you can move to the Monday, Wednesday class, that would be great. Now, you don't have to be on waitlist to move to the Monday, Wednesday class. If you're even enrolled and you go like, oh, I would much rather being able to sleep a little bit longer on Tuesdays and Thursdays, and I do have that time slot open on Mondays and Wednesdays, you can go ahead and transfer to the other class. Just drop from this one and then enroll in the other one. Okay? But other than that, I can't really add everybody on the wait list to this class because there's just no way I can fit this many students in the lab. Is that okay so far? All right? Okay. So given that, I'm just going to pass the row sheet. Even if you're on wait list, you still want to kind of initial your name, on the row sheet, so just so that I can tell who's here and who's not. So I'm going to start with you. Go. Thank you. All right. So I'm just going to get a sense of how many people can move to the Monday, Wednesday class. So how many people think that you might be able to move to the Monday, Wednesday class? Doesn't matter whether you're enrolled or on wait list. Nobody. Okay. Yep.
It ends at 1:30, you said?
Yeah. So 1:30 is the lab. So the lecture starts at 10:30, and then the lab starts at noon. Let me double check that.
I used to, but I have a class at 12:45.
Okay. Let me just double check that. So yeah, so the lecture starts at 10:30, and then the lab starts at noon, and it ends at 1:30. Yeah, unfortunately, they don't have a lab big enough to house all the students in this classroom. I'll check with the dean and see if they have the next lab because we are gonna in 409. So if the lab right next to 409 is also open, I can kind of go in between the two labs. That's not a problem until it starts to rain. But I can check with the dean. But for now, if you can transfer to the Monday Wednesday class, that would be great. All right. Final exams. Okay, I'm hoping you guys all know how to find out when on which day and when on that day the final exam is going to be. Am I correct about that? Okay. So basically, I have a link here, so it's easy to kind of go to the final exam schedule. And all you have to do is to find out, map here. Okay, so day classes beginning. This class starts at 9 a.m. and it's a Tuesday, Thursday class. Look it up and then find out on which day the final exam is going to be and what time the final exam is going to start. Okay, so I'm going to count on you guys to be able to figure that out. Okay, I do not move my final exam time from the scheduled time, so it's really just based on this schedule. All right. With that out of the way, I think we can start on the actual content of this class. So I'm moving a whole bunch of stuff out of the syllabus discussion so that I can start on the content stuff earlier. So what we'll do today in class is I will start with this little kind of lecture thing. There's no textbook to buy. Okay, I write all my material, but because I don't have an editor, because I just write this stuff, nobody pays me for that, so I cannot afford to have an editor. So if you find any mistakes, spelling mistakes, grammar mistakes, content mistakes, and whatnot, send me an email. Okay, it's very easy for me to change and correct my notes. Okay. All right. So this is your reading material. All the reading material is already on the website. And if you have time to read ahead of the class, that's fine. It's a good thing to do. So all you have to do is to read it in this particular sequence. I just follow this particular order when I talk about the topics. Is that okay? So each one is kind of like the syllabus, the common part of the syllabus. So each one is basically available as PDF and also as HTML. In class, I use HTML. But if you want to print a copy and put it into your binder, the PDF may be a better choice. Okay. I also want to let you know ahead of time, in the past at least, all my exams are open book and open notes, which means if you print it out, you can mark it up on a piece of paper and then bring it with you to the exams. Okay? Because my emphasis is not how well you can memorize individual data, facts, and stuff like that. It is about how well you can apply the knowledge to solve problems. So I don't see any really important point for you to memorize everything that is in my notes. Okay, you can bring your own notes. You can bring my notes. If you find textbooks that are useful, you can bring those textbooks. The only restriction is no electronics other than a scientific calculator during the exam. But as far as content is concerned, you can use just about any content. Yes?
I like to read a textbook sometimes. Is there any you'd recommend?
I'll get back to that, okay? There is one textbook that kind of jives with what I talk about in class, but I can't remember the name of the textbook, so I kind of have to dig it up. Mm-hmm. All right, so let's go ahead and start with this module. The module number is not really particularly useful. It's nothing more than an ID, so each module has its own number. So what we'll be talking about today, has to do with physical states, has to do with the representation of values that we call numbers. Basically Boolean stuff, okay, because what is true and what is false. How do we represent those as physical states? And we'll start to touch on computers in today's class. Now, for those of you who like to look at an kind of overarching, overview of a class, what I want you guys to be able to do at the end of this semester is to look at a C++ program, okay? Maybe just a single subroutine in C and C++. And then you can basically get the X-ray vision like Superman, okay? And you can look down one level and you see assembly code. You look down one level and you see the binary opcode, okay? You look down one level, you see the overall processor architecture. And then you look down one level, you see the ALU, and you can see inside the ALU, oh, this is the adder, this is the subtractor, and so on and so forth. You look into the adder, you see gates, you see AND gates, OR gates, NOT gates, and so on. You look into an AND gate, then you go like, how do I implement an AND gate? We can use transistors to implement an AND gate, so you start to see the transistors, okay? And we stop there, okay? We don't talk about device physics in this class, but we do get all the way down to transistors. So that's kind of what I want this class to be able to do, is to give you that X-ray vision capability so that you can actually see the entire stack of layers of knowledge when you look at a C++ program, all the way down to transistors. Is that okay? All right. So it's kind of nice to kind of keep that in mind as we go over these topics. So we start with physical devices that were used. Some of these were used to implement computers. So at the end of World War II, electromechanical devices were used as components of computers. Okay, the most you can actually watch movies to see how these things work. So if you look up imitation game, the imitation game, let me see if they have a picture of the computer. In that movie. Yep, there we go. So we got quite a few representative pictures. And click on that. All the advertisements. So can I display just that? Yep, there we go. Get rid of this. There we go. So behind the actor, this is a electromechanical device. What do you see? You see a lot of rotors, right? So the rotors, by the name, what do you think rotors do? Why do you think it's called a rotor? It rotates, okay? But it rotates, because it is actuated by electromechanical devices. Okay, so it clicks and it turns, okay? When they turn, the connection through this particular rotor would change. In other words, it reroutes, okay, how things go in and how things go out. It changes the connections. And that is how this kind of computer work. Okay, it's electromechanical by nature. Do you guys remember the name, for those of you who watched the movie, do you remember the name of the machine behind this actor? Not the Colossus. Yep. The Enigma machine is what this computer is trying to defeat. So the Enigma machine is the device that encrypts, and that's relatively small. It's about the size of a typewriter, because when you press a key, another light will light up. So it maps, what you're typing to different characters. Okay, and this machine is responsible to decrypt the encrypted transmissions. So do you guys remember the name of this computer? BOMBE. Okay, and I'm not 100% sure how it's supposed to be pronounced. I'll call it a bomb computer. So basically, this is the decryption machine that Alan Turing, this actor, what's his name? Yep. So he's trying to portray that particular computer scientist. So Alan Turing was the father of computer science. Without him, we wouldn't really have computer science as we have today. But there were a few other people along the way that also contributed very significantly to computers that we have today. But he's the guy who started it all. Okay. So this is a mechanical, electromechanical device. So if we go back here, what do you think is going to be some characteristics of electromechanical devices? In other words, if I were to implement my Fitbit using electromechanical devices, what do you think is going to happen? Yep.
They have to have transistors at some level.
Nope. There were no transistors with that particular computer. It's purely electromechanical. Huh? Nope. That computer did not have vacuum tubes. Yep.
It's going to get a lot bigger because it's a lot more moving parts.
Yep. A lot more moving parts. And what about? Yeah, go ahead.
Will it heat up?
It will heat up more because in order to turn electricity into actual motion, what do you need? Or one of the many ways, but it's the most common way to turn electricity into motion. Magnetic stuff, okay? Coils, okay? And every time you pass current through a coil so that you can have a magnetic field, what do you end up with? How many people have taken physics? Okay, so in physics, is there such a thing called a perfect conductor where it has no resistance? No. Superconductor are close, but they still have resistance, just very, very small. Okay? But we don't have that. I cannot wear a device on my hand that has supercooling for superconductance, right? So we just have regular copper, which has resistance. So what happens when you pass current through a conductor that has some resistance? It heats up, exactly. Most of the energy is dissipated as heat, okay? So these computers tend to run hot, okay, because they use a lot of energy to move parts and so on and so forth. And then the second part is, do you think these computers can be fast? What is the limiting factor? The rotors, right? You can't really turn the rotors beyond a certain speed and still be reliable. So they're slow, they're bulky, they use a lot of energy. But guess what? At the time, this is the kind of technology that was available, and they had to do it, using only these components. Okay? So that's electromechanical devices. And then vacuum tubes did exist during that time, but the bomb machine was not using vacuum tubes. So vacuum tubes are interesting. They are very different from electromechanical devices. Okay, let's take a look at some pictures of a vacuum tube. So if you right-click on the link, typically I would use a Wikipedia page so that I can kind of sidetrack to different concepts. So these are vacuum tubes. They look like light bulbs, and they kind of light up like a light bulb too, except they're not really bright like a light bulb. They give you a kind of low reddish kind of glow, because the idea is you have to heat up the cathode in order for electrons to be free, okay? So once you have electrons that are free from a heated, metallic surface, then when you have charge on the heated plate that is negative and a positive charge somewhere else, the electrons would actually travel through vacuum from the heated plate that is negatively charged to the plate that is positively charged, okay? But it doesn't go in the opposite direction. So these devices, you can see that some of these have, relatively few contact points, and some have more contact points. But the idea is there's one particular device that is important. So if we go back to the module, there's one particular device that is particularly useful. It's called a triode. And a triode looks like this. And here's a full explanation of how it works. You do not have to study the Wikipedia pages, even though it's linked. I just want to include it just so that people who are interested can go look at it and go like, oh, I need to find out how it works. Okay, and this explains how it works. But basically, you look at a triode like a valve. Okay, a faucet. Okay, so you turn it on. Okay, it allows flow. You turn it off, and it stops the flow. It disconnects. Is that okay? But there's one big difference between a faucet that you can turn as opposed to a triode. Okay? That main difference, the most important difference, is if you're dealing with a faucet, you are turning it on and turning it off, right? but you are not hydraulic. You are not made out of, you're not water-based. Okay, so the mechanism, the physical mechanism to actuate and disable the valve is different from the kind of physical quantity that it is controlling. Am I making any sense? A triode is different because it's using electricity or electrical charge to control the flow of electricity. Now, why do you think that is important?
You don't have to pump anything else, just electricity.
Exactly. And whatever it is switching can then be controlled, can then be used to control another triode. Okay? And then the second triode, whatever is switching, can be controlling yet another triode, or and so on and so forth. So this is why it is important for us to find devices where the controlling mechanism or the physics of the control mechanism is the same as what it is controlling. Is that okay? So if you can invent, okay, a transistor or a valve that works on light, okay, you use light to turn on and turn off the device, but in return, that device allows or disallows the flow of light, that can be very useful. Okay? Electricity is what we use for the most part these days, but any type of flow that can be controlled like this using a valve technology can potentially be used to implement computers. Are we good so far? Okay. All right. So vacuum tubes are kind of cool because they are one big step ahead of electromechanical devices. Why do you think that is the case? Why do you think people look at vacuum tubes and go like, wow, this is really cool compared to electromechanical devices? Yes? Exactly. So it can be a lot faster because it takes much less time for a triode to turn on and turn off as opposed to the rotation of a rotor to change connection. So that's why vacuum tube-based computers can operate a whole lot faster compared to electromechanical devices. But they still have two problems. One is they're still kind of pretty big because each vacuum tube is a light bulb. Okay, it's it's not that small. And then the second one is it is still a power hog or energy hog. What do you think is taking up so much energy with these vacuum tubes? It has to do with the device itself. There's no way around that power consumption part.
It relies on resistance?
Not directly, but it does use resistance in order to, remember what I said, it looks like a light bulb with a light, kind of like a dim glow to it. That part is necessary because in order for vacuum tubes to work, in order for electrons to be able to go from one surface to another surface through vacuum, it has to be heated up. The metallic surface has to be heated up. That is why vacuum tube is not energy saving, okay? Because you have to heat it up in order for it to work. Is that okay? But they are faster. So there are examples of computers that are vacuum tube based. So I heard a little bit earlier, Colossus is the name of the computer. So the Colossus is another computer that is designed to do decryption or crack encryption. But the target that it targets a different encryption mechanism. The bomb computer, BOMBE, was designed to crack encryption by the Enigma machine. The Enigma machine is widespread because it's a very small device, it's very portable. So the Army, the Navy, the Air Force can take that device and field deploy anywhere they go. But the encryption scheme is relatively simple, and that's why they can use an electromechanical device to crack the encryption. The Germans or the Nazis actually had another cipher. It's called the Lorenz cipher. It is a lot more complicated, but it is also a lot bigger. So this can only be used between main offices of the military, cannot be field deployed because it's just too big, it takes a lot of electricity. But in order to crack the encryption by the Lorenz cipher, you also need a faster computer, and that's why the Colossus was invented to crack the encryption of the Lorenz cipher. So it's really interesting, in how technology advances so rapidly when there's war. Not that I'm promoting it. I'm just observing. Based on the observation, there's a lot of advances in technology. When there's a need to do it. Are there any questions? No questions? Okay. Are there any audio files here who has a vacuum tube-based amplifier? Because I think some people do that even today. They design amplifiers for audio purposes using vacuum tubes, and I think they're pretty expensive too. They're pretty cool to look at because they have that little glow, and you can actually watch it. It's actually entertaining. All right, so we are moving on to transistors, which is the current technology that we have. Now we're still using transistors, even though the transistors that we have now are very, very small. We are talking about 14 nanometers now. But nonetheless, the physics is still based on the p-n junction. So this paragraph talks about how the mechanical or the physical part works with semiconductors. Okay, so I'll just kind of go through that a little bit in this class, just so that you guys have a vague idea of how it works. All right, so semiconductor is based on, what do you think it's based on? Why do you think we call that portion of the Bay Area the Silicon Valley? What material, what element do you think we use in semiconductors? Silicon. Okay, so silicon is Si, and how many electrons are on the outermost orbit of a silicon atom? There are 4. Okay, so that means it kind of looks like this. Okay, for those of you who have taken chemistry, you know how to read this, right? This is actually extending out of the plane. This is going into the plane. So we have another Si here, another Si here, another Si here, another Si here. So it makes a crystalline structure, kind of like diamond. That cannot be conductive because there are no free electrons in this particular structure. Every single electron is used by sharing with whatever is next to it to form the covalent bond, and as a result, the electrons are not free to move around. If you do not have electrons that are free to move around, it does not conduct. Okay, it doesn't conduct electricity. All right, so silicon by itself cannot conduct. Wait, but how is this related to semiconductors? And what is that name about transistors? So we'll first look at the name transistor. For those of you who have taken physics, does the name transistor remind you of a particular really common device in circuits? Some sister? Resistor, right? Okay. So what does a resistor do? It's called a resistor because it resists, right? Okay. What is it resisting? The flow of charge. Okay, very good. So, okay, so a resistor resists the flow of charge, but it does so in a consistent, constant way, right? So if you don't take into the factor of temperature changes the resistance of resistors, it's kind of like constant, okay? A 20 ohm resistor is always 20 ohm. It always resists the flow of current or resists the flow of charge kind of the same way. Cool. So why do you think a transistor is called a transistor? It allows a change of the resistance. Right, so it's kind of like a variable resistor, except the control part is also done done by charge or current. Okay, so it does meet that requirement that we talked about a little bit earlier. Do you guys remember? A little bit earlier, we are looking for devices where the control physics is the same as the controlled physics. So a transistor meets that requirement because we are using either charge or current to control the flow of current. Okay, so that's kind of cool. So now getting back to here, so everything about transistors, doesn't matter what kind of transistor, they all rely on what we call a p-n junction. So what is a p-n junction? Okay, I'm not going to get too much into the physics here, but I'm going to say, what if we change this to a p, to phosphorus? How many electrons are at the outermost orbit of a phosphorus atom? 5. So when you stick like a very small amount of phosphorus into silicon, guess what's going to happen? It'll be forced into the crystalline structure. But at the same time, it only takes 4 electrons to form, to hook up to its neighbors. There's 1 electron left that has got nowhere else to go. That electron becomes a free electron. And now your silicon structure is no longer an insulator, it is now conducting. That's kind of cool. And they have other elements where they create holes instead of free electrons. But a hole is also moving, so it can also be used to carry charge. So P is for positive, N is for negative, and that basically forms the 2 materials that we use in semiconductor. I put this onto a whiteboard, because it's not going to be quizzed, okay? Just for those of you who are interested. So when you have a P and an N material, okay, it naturally forms an area here that is neutral. So the free holes of the P material is going to cancel out the free electrons from the N material. So this portion here is actually non-conductive. All right? But if you put a charge on the 2 ends here, if you put a positive charge on this side, and you put a negative charge on this side, then the barrier, or this portion, will get very, very small until it is actually so small that it allows flow to go, it allows charge to go through. Okay? On the other hand, if you flipped it, and you say, I'm going to apply a negative charge on this side, and a positive charge on this side, then what happens is this barrier increases. The thickness of that barrier increases, so it does not allow the flow of charge anymore. Okay, so that's the basic principle of how a p-n junction works. For those of you who are going to become electrical engineers, you will actually have to take a class that talks about just this, the physics of a p-n junction and how you calculate all of these things. Okay, but for this class, we are not that concerned about the physics. We are more concerned about the characteristic of the devices. Okay, so that's discussed down here. Well, we'll get to that part. So before we get to that part, I have to talk about physical states. Okay, when you look at a device, okay, you can say, okay, when you look at a faucet, okay, and you don't say, you don't consider, a faucet is halfway open and halfway closed, okay? What are the 2 states that might be of interest to you when you look at a valve? Doesn't matter what kind of a valve it is, faucet can be a relay, can be a transistor, can be a vacuum tube. What do you think are the 2 states that you might be interested in? If it, yeah, exactly. Is it open, which means it is actually not letting flow through, or is it closed, which means it is allowing flow to go through. Okay, so it's kind of counterintuitive. The term open means it is disconnecting. The term closed means it is allowing connection. Okay, so those 2 states are important whenever we talk about valves or things that can switch. Okay, so that's physical state. Okay, transistors, have those 2 states. A faucet has those 2 states. A relay has those 2 states. Vacuum tubes have those 2 states. Okay? 2 states. What do you think it reminds you of? Zeros and ones, true or false? Okay? How do we call things that are true or false in CISP 360? They're Booleans. Okay? All right, so now we can start to think about, we can map, okay? If a valve is closed, we'll call it a 1 or true. If a valve is, did I say open or closed? If it's closed. Okay, so closed is a 1, open is a 0. So now we can map, we can assign meanings to the physical state of devices. Is that okay? All right, so that is kind of important. So that has to do with Boolean values. So we are basically just that's how. So now we are moving on to actual transistors. Are there any questions about the mapping of physical state to meanings? If a valve is closed, we call it a 1, or we can call it true. If a valve is open, we call it a 0 or false. Is that okay? All right. Or we can also use the presence of a charge or the absence of a charge. If there's a presence of a charge, we call it a 1. If there's an absence of a charge, we call it 0. We are just assigning meanings to physical states. Is that okay? All right. So what we'll do now is to look at two specific types of transistors. This is an N-type transistor. Okay, right here. There are several ways to represent an N-type transistor, but this is just one of them. There are 3 terminals. Now, how do you distinguish terminals from each other? Well, the gate is easy to distinguish because the gate is the one that's sticking out to one side on its own. That's called a gate, which is also simplified to just G when you look at the symbol. And then there are 2 terminals on a line. They seem to be connected, okay? But there's some funky stuff going on here. We'll explain that later. But there's also an arrow, which helps you distinguish those 2 terminals. The arrow is telling you how charge is flowing. And charge always flows from source to drain. So the bottom, the south one, is called the source, abbreviated to S. The north one is called the drain, abbreviated to D. Is that okay? So let me just kind of go through this one more time. Okay, how do you identify the 3 terminals of an N transistor? The gate is on its own, and when you look at the symbol, it is not even quote unquote physically connected to the rest. And then for the other 2 terminals, the arrow indicates the flow. The flow always goes from source to drain. Yep. It's neither. We only look at it as charge. Okay, but so depending on the type of the transistor, the charge can be negative or positive. Okay. So this is an N transistor. So the next question, once we have identified the names of the terminal, now the next question is, how do we turn it on? How do we turn it off, right? So the gate is the control. If the gate has a positive voltage, then an N transistor turns on. If the gate has 0 volt, then an N transistor turns off. Is that okay? So I'll say that one more time. If there's a positive voltage present at the gate, an N transistor turns on, which means it closes, it completes the circuit. On the other hand, if the gate has 0 volts, then the transistor, quote unquote, turns off, which means it disconnects between the source and the drain. Is that okay? Cool. So now we look at the other, yeah, go ahead. It does not. It's only the charge. And that's why you see there's no actual connection to the rest. Yeah. So it's basically the presence or the absence of a positive charge, okay, but there's no quote unquote actual current going through the gate. Okay. It's because this is called a field effect transistor, or FET, instead of a BJT or bijunction BJT, bijunction transistor. So it's a different type of a transistor compared to the other type. Okay. But as far as we are concerned, we just need to know charge at the gate controls the state of the transistor. Okay. So the next one is called a P transistor. Let me zoom out just a little bit so that we can see both of them. Okay, that's good. What do you think is the main difference other than the orientation? Remember, we can always rotate and mirror so that the arrow can point in any direction we want it. So what is the only main difference between an N transistor versus a P transistor? Yep.
It's closed without a charge, and it's open when it has a charge.
Right. But from the schematic from the picture, what is different?
Oh, a little bubble.
The little bubble. Very good. Okay, so the bubble is the only difference graphically between an N transistor versus a P transistor. A bubble in a schematic that we use today, used in this class, means negation. Okay? So what do you think is the behavior of a P transistor? When there is 0 volt at the gate, what do you think happens to the device? The circuit is closed, or the transistor is quote unquote on. Okay? If there's a positive voltage at the gate, then it is off. Okay? It disconnects. So it's opposite to an N transistor. Right? Because with an N transistor, the presence of a positive charge turns on the device, it connects. But with a P device, the presence of a positive charge turns off the device, it disconnects. Is that okay? All right. Now, this is the important part. When we talk about charge, with an N transistor, we're always talking about negative charge. It's the negative charge that goes from the source to the drain. When we talk about the P transistor, P stands for positive. So the flow of charge is with respect to positive charge. Okay, so it's positive charge going from here, from source to drain. So are we kind of doing okay so far with this? Cool. All right, cool. So now that we have these devices, we'll make a circuit like that. Okay, so this is a circuit. It has 4 transistors. And I'll just give you guys a quick quiz here. What are the types of Q1 and Q2? Are they P transistors or are they N transistors? They're P transistors because there's a bubble. Okay, very good. And then Q3 and Q4 are N transistors. Very good. So let's also identify the other symbols in this circuit. This triangle pointing to north is what we call a supply voltage symbol. It is positive. Okay, so that's a source of positive charge. Look at this as the positive terminal of a battery. Okay, this part here, the bar, that's all the way to the south. That's called a ground symbol, which also represents, basically 0 volts. Okay, is that okay? 0 volt, some kind of positive voltage. We don't know exactly how much, but it's not important. And then we have pins. The squares are input pins. Okay, those are the terminals where you can apply a charge to. So you have control over the charge at the square pins, the input pins. The little circle is the output pin. It's not a place where you can apply a voltage or a charge to, but it's a place where you can put a multimeter and check. Okay, what is the charge at this point? Okay, is it a high voltage? Is it a low voltage? Okay, so this is what you read out of this. This is what you specify. If you look at this as a function in C and C++, the little circle is kind of like a return value of a function. The 2 square pins are kind of like parameters to a function. Is that okay? All right. So now the question is, what is this circuit going to do? Yep. It's a NAND gate, exactly. But how does it work? So we'll go ahead and play out in some scenarios. So I'm going to write it out in class, but the rest of the notes actually talks about each possible combination of the input. So you don't really need to write down a whole lot, also considering this is still being recorded. So what I'll do is I'm going to open up a text editor, put it on the side, and then we'll say, okay, what if X is 0 volts or low voltage? Y is a 1, which means it is high voltage. So we want to identify what's going to happen to Q1, Q2, Q3, Q4, and then eventually what the output pin is going to experience. All right, so we'll do this analysis step by step. which also means I need to go over what is a dot here and what does it mean without a dot. So without a dot, which is kind of like this part, it's flying over. The two wires are basically quote unquote flying over each other. They are not electrically connected. Let me just point out which part I'm talking about. So with this part here, these two wires are flying over each other. They do not electrically connect. On the other hand, when you see a dot here, it means they are connected. So that means this is a junction that connects to the pin Y. It also connects to the gate of Q2, and it also connects to the gate of Q4. Is that okay? All right. Okay, so now that we kind of know how to read the schematic, let's go ahead and figure out what is Q1 going to do in this particular scenario. So is Q1 connecting or disconnecting? Q1 is a P transistor. The gate of Q1 connects to X as an input pin. X as an input pin has a low voltage. So what do you think a P transistor does when the gate is experiencing 0 volts? It turns on, right? It connects, okay? So we'll just say that Q1 connects. What about Q2? Q2, the gate of Q2 connects to Y, and Y has a high voltage. So it's going to be, it's not connecting, it disconnects, okay? So we'll just say disconnects. And then Q3 and Q4 are kind of the flip side because they're AND transistors. When you look at Q3, the gate of Q3 connects to X. X has a 0 volt, so Q3, does it connect or not connect? It disconnects. Okay. And then what about Q4? Q4 connects to Y, which has a high voltage, and Q4 being an AND transistor, if the gate is experiencing a positive charge, it is connecting. Okay. All right. So now in your mind, what you need to do is to say, okay, something that's connecting like Q1, you can just draw that line, okay? Because it's just connecting. Okay, it is as if the device is not there in place, you put a copper wire. Okay? Q2 and Q3 are disconnecting, so you just take them out completely. It is as if there's nothing there. Is that okay? So now what you need to do is to look at the output pin and you ask, is the output pin not connecting to anything, or is it connecting to the positive voltage source, the supply voltage, or is it connecting to ground? Those are the questions that you have to ask. Okay? So let's try to solve this puzzle. So you start with the output pin. You go here, go like, well, I got two ways to go. I'm going to explore the right path first. So you take a right turn, and now you have a branch again. So let's say you want to go for the right branch again. So you go here, but then right now you get to a dead end. Q2 becomes a dead end because that transistor is not connecting. That path is as if it's not there. Is that okay? So what do you do with a dead branch? Well, you turn around. You turn around, you get back to this junction, go like, I got one more path to explore before I get home. So you go to the other path, and you go like, okay, Q1, are you connecting? It is. So you just go here, and you follow that path, and you end up at the supply voltage. So you know that the output pin is connected to the supply voltage. But it doesn't hurt to analyze the other way, right? So you take this, you look at the output pin. This time you make a left turn because you want to make sure that we don't have a path to go to ground. Because if you have a path to go to supply voltage and you have a path to go to ground, we have a problem. Why do you think that's a problem? It's a short circuit. What happens when you have a short circuit? No, the battery is the last thing to blow up. The transistor blows up. The transistors blow up, okay? Because the transistors are much smaller, having a much smaller thermal mass than your battery. We are talking about a transistor that is only about 14 nanometers across, as opposed to your battery pack, which is a lot bigger. Okay? So we want to double check. So now we go from the output pin, make a left turn, go to Q3. Q3 disconnects. It is as if this thing is not here. We hit a dead end. That is what we want. Okay? Cool. So that means the output is 1 or 0. 1 is high voltage and 0 means 0 volt. Does it connect to ground, 0 volt, or does it connect to the supply voltage, which is positive? Positive, we'll call it 1. Is that okay? The other one, the next one is, let's make both of them 0 and see what happens. Okay? So if both of them are 0, what happens to Q1? Connects. Because Q1 is a N transistor, when the gate of an N transistor is, Q1 is a P transistor. When the gate of a P1 transistor, gate of a P transistor is a 0 volt, the device turns on. Okay? Same thing with Q2. Q2 connects to Y. Y is also 0 in this case. And then Q3 and Q4 both disconnects. So now the question is, what is the output? So in this particular scenario, you do the analysis the same way. It's a little bit different from before, but the outcome is the same. So you start with the output pin, you make a right turn, then you make another right turn. Guess what? This time it connects to the supply voltage. But you can also make a left turn after the first right turn. It also connects. It's no big deal. You just have 2 parallel paths to connect to the supply voltage. Okay? It's not a problem. We have a good connection to the supply voltage. You start with the output pin, you take a left turn. Q3 is disconnecting already. I don't even need to know what Q4 is because Q3 is already disconnecting. Not a problem. We do not have a path to go to ground. So we have a really good path to connect to the supply voltage, so the output is a 1. Okay? So the next one is x equals 1, y equals 1. And let's see what's going to happen. It's kind of the opposite of the other one. Q1 disconnects because Q1 is a P transistor. When the gate of a P transistor has a positive charge, the transistor disconnects. Okay? Same thing with Q2. It also disconnects. Q3 connects because it's an N transistor. Q4 is also an N transistor, so that's why it connects too. So now let's do the analysis first. We start with the output pin, make a right turn, make another right turn. It's disconnecting. We hit a dead end. Turn around, make a left turn instead. That's also a disconnect. It is also a dead end. Is that okay? So we have no path this time whatsoever to connect to the supply voltage. Well, that does not automatically mean the output is a 0, okay? Because it can be what we call floating. It doesn't connect to either end, okay? So we want to double check and see whether it does connect to ground or not. So now you start with the output pin, make a left turn. This time Q3 connects. We are here between Q3 and Q4. Q4 also connects. So now we have a complete path to ground, which means the output pin is now electrically connected to ground. Ground is 0 volt. How do we represent 0 volt? Or what is 0 volt representing? 0 or 1? It's representing 0. Okay, so it's a 0. Like so. We only got one more possible input, which is x equals 1, y equals 0. I'm not going to go through the math here because this one is symmetric to the first case. So what do you think is the output? The output is 1. Very good. Okay, because you can go through the actual analysis, but the outcome is the output is 1. Is that okay? So by analyzing the circuit, we kind of know the behavior of this circuit at this point, which is kind of cool because now we can kind of condense the whole thing into a truth table and see whether we can recognize something out of this truth table or not. So the truth table has x being an independent variable, y being an independent variable, output being, the dependent outcome of the gates. So 0, 0 has an output of 1, 0, 1 has an output of 1, 1, 0 has an output of 1, 1, 1 is the only time when we have an output of 0. Okay. So you look at this truth table, and you go like, do we recognize this as one of the logical operators in C and C++? It kind of looks like an OR gate, because if you look at the truth table of an OR gate, it has 3 1s and 1 0, right? But it's not. This is not an OR gate, because if it were OR, 0 or 0 would have given you a 0. Okay, darn it, doesn't work. It looks also like an AND gate, because with an AND gate, the only one that is different is when both inputs are 1s, and then for everything else, they have the same output. Except this is the flip side of an AND gate. Because if this were AND, we would have 0, 0, 0, and then a 1. This is giving us exactly the opposite of that. We're getting 1, 1, 1, and then a 0. So what do you think is this thing? He mentioned it earlier. Yep. It's the negation of an AND. Yep, that's right. So in C++ notation, we can now say this is the logical negation of x and y. So if you were to go through the math, the actual Boolean expression, you would have come up with 1, 1, 1, 0 by evaluating this expression. Is everybody convinced that the negation of x and y would give you 1, 1, 1, 0 as a column? Okay, cool. So we can keep calling this negation of AND, negation of AND, negation of AND, but very soon you will realize that engineers are lazy people. They don't like to say negation of AND. They want to call this NAND, N-A-N-D. Okay, so it's a NAND gate. Is that okay? I don't see anyone going like, whoa, this is cool. Okay? Now, to me, this is cool because we started off with physical devices like transistors and whatnot, and we ended up with C code, expressions that you already understand in C and C++. But somebody's going to complain and go like, yeah, but we have never used a NAND gate ever in C and C++. In fact, there's no single operator called NAND in C and C++. So what is the big deal here? Well, the big deal is given the NAND gate construct, you can reconstruct all of the other operators that you already know. It is the universal Boolean operator. Nobody's convinced. That's okay. That is okay because I want to be able to explain it. The worst thing that can happen is all of you go like, yeah, we know that. Then I don't have a job anymore. All right. So here we start to talk about symbols and stuff like that. Okay. All right. So this symbol, the up arrow thing, is used to represent NAND, N-A-N-D, or the negation of AND. I think the reason has to do with this symbol here, the inverted V, is mathematically called the conjunction symbol, or AND. Okay, so by adding a bar, a vertical bar, to mean negation, so that's why the up arrow symbol is representing NAND. Okay, that's just what I think why they chose that symbol. Is that okay? All right. So the first thing we need to do is to say, can we express just logical negation, not using NAND? In other words, if I really just want to express the negation, logical negation of x, this little symbol here is the mathematical symbol for logical negation. So if we just want to say not x, is that the same thing as x NAND x? What do you think? You guys are not, you don't seem convinced. All right, that's fine, okay? If you're not convinced, if you're skeptical and you are kind of go like, I don't trust Tech, with his stuff, that's actually a good thing. So now the next question is, how can you verify and go like, not X is really the same thing as X NAND X? How can you prove that? Well, truth table. So what you do is you make a truth table. We only have one single independent variable in this case. We have the usual negation of X, which you already know. And then we have the NAND operator, but I'm going to write the NAND operator as the negation of AND, just so that it is matching what you already know from C and C++. Okay? X is Boolean. It can either be 0 or 1, true or false or true. So when X is false, what is not X? True, okay. When X is true, what is not X? False, okay, no big deal. So now you plug in X into this more complicated equation or expression. X is false. False and false is false. Not false is true. Very good. So we put a 1 here. And then on the next row, we do about the same thing. X is true to begin with. True and true is true. Not true is false. Cool. Well, there you have your proof. By using a truth table, you have examined every single input possible to the operator. And if two columns, okay, not X versus X NAND X, if they have identical values, that means those two expressions are truly equivalent. They mean exactly the same thing. Is that okay? That's negation. Let's try out to find out what is conjunction. Okay, so we have X. This time we have two independent variables, X, Y. We want to express X and Y, and we have to figure out how to do that. So X can be false or true. While X is false, Y can be false or true. While X is true, Y can be false or true. And we know this truth table fairly well. So they're all false except for the last row, which is true. Okay, so that's the easy part. The difficult part is now saying, if we only rely on NAND, can we come up with exactly the same column? That's the question. So I'm going to propose and say we can have X NAND Y, the whole thing, NAND, X NAND Y. Okay. The notes has it simple because the notes uses the NAND symbol. But if I don't use the NAND symbol, it gets a little bit complicated. Because we end up with a blah, 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 NAND, and blah, blah, blah. And then inside each one looks exactly the same. Not. These are the NAND operators. I'll backfill what is going inside. Okay. So backfill what is inside is just X, Y. So this is X. This is Y. This is X. And this is Y. So is everybody convinced that this whole complicated expression is really the same thing as X NAND Y, the whole thing, NAND, X NAND Y, the whole thing? Yep. Oh, you want? I can move the bottom. In the new STEM building, I have specifically requested that they put the projection screen to be higher up so that everybody can see the entire screen. Because otherwise, the bottom part of the screen is useless. They might as well just cut it, right? All right. So is everybody convinced that this complicated expression is really just X NAND Y, the whole thing, NAND, X NAND Y? This is X NAND Y as one thing. This is X NAND Y as one thing. And this is the outermost NAND applied to the whole thing. Is that good? Okay. So we'll try to figure out the values. I mean, obviously, you can write a program to test this, right? When x and y are both false, false and false is false, false and false is false, not false is true, not false is true, true and true is true, but not true is false. Okay, so we'll go ahead and work this out. This is false. The next one, we have at least one input being false, so that means x and y is false, x and y is false, false and false. Not false is true, not false is true, true and true is true, not true is false. And the next one is symmetric. It's kind of like the mirror image of this one, so it's also false. The last one, where both x and y are true, then we end up with true and true is true, true and true is true, not true is false, not true is false, false and false is false, not false is true. Here we have the proof. Sounds pretty simple. It is simple. All right, so the next one is even more complicated because it is OR, and it requires the use of De Morgan's law, and I'm not going to get into De Morgan's law, but the bottom line is x or y can be expressed as x NAND x, the whole thing NAND, y NAND y. And you can do exactly the same thing with a truth table to verify that that is the case. Okay? So this is pine needle. So if you zoom out just one level and look at the pine tree, what is the significance of all this stuff here? Ignore the actual derivation and just focus on x or y can be expressed as some silly expression involving only NAND. What is the significance of that? We only need NAND. We don't need no stinking or AND, or not. We just need NAND. Okay, so that's part of the pine tree. What is the other part of the pine tree? We can implement NAND using transistors. Can we buy transistors at Fry's or other places? Yes, they're actual physical devices. Okay, so this is big. This is big because every single Boolean operator that you have learned in C and C++ can now be implemented using transistors. I mean, is this really the best use of your transistors? Not. That's not the case. But can it be done? Yes. Okay, so we are getting, this class is kind of like a bottom-up thing. We start at the very bottom, the transistors. Now we have the vocabulary to express all the common logical operators that you already know. Okay? So the next step up is to look at how we represent values. Okay, using numbers, right? We are used to decimal numbers because, for whatever reason, we got 10 fingers, which is not good. Okay? We'll see why it's not good. So we want to look at ways go like, okay, but how do we use transistors, the states of transistors, or voltages, to represent values? How do we represent the quantity of 23 when you only got a whole bunch of transistors? Okay, so that's the next step up. Now that you can represent values, what do you want to do with values? You probably want to do addition and subtraction, right? So how do we do addition and subtraction, but only using transistors? So that's what we're doing in this class is we start with the bottom layer, which are the transistors, the physical states, voltages, and stuff like that. And then we go up and up and up and up. And eventually, at the end of this semester, you'll be doing recursive algorithms in C using the processor that we're going to use in this class. But everything can translate all the way back down to transistors. All right? Okay, so it's 10:20 right now. I'll give you guys a 10-minute break, and then we'll meet over at the lab. And as I said, the lab only has 29 seats. Okay, so if you are not in class, okay, if you're not enrolled, please do not take up a seat with a computer because you wouldn't have an account to work with the material that I have today anyway. Okay, but you can watch the other person doing it.